Okay, so just for your homework, there was really just these science understandings that you needed to be made aware of and to be familiar with. The thing I've mentioned before is that there aren't specifics that you need to know, but we're going to go through some specific examples, and that's there to help us better understand, especially when it comes to looking at stages in the production of metals and understanding why certain processes are used for the production of some metals, whereas other types of processes are used for other metals. And it's all based around metal reactivity. What I will do though is get you to know some specifics, because it's going to help you be able to identify what method of reduction you would employ given the reactivity. And it's based around an image I showed you in the previous lesson. So I'll come to that in the end. So in terms of metal production, we know that many metals will exist combined. We say they exist as minerals in the Earth's crust, and they're contained within ores. So minerals would be naturally occurring compounds. Many examples would consist of silicates and aluminosilicates. So we know that they're sort of ionic compounds that consist of a metal component and with a sort of anionic component, which will be your silica or aluminosilicate. So the key thing is that it has a definite chemical composition. That means we can represent it with a formula. In terms of what we dig up from the ground, that's what we call an ore. And so it's a naturally occurring solid mixture where the metal concentration is high enough to be viable. That means we can essentially mine it and we can process it, and it's going to actually be commercially viable, economically viable. It's essentially going to make money for those mining companies or those metal production companies. In terms of the processes, it can involve all or a combination of some of these processes. First one, you'd have to extract the ore. Second, you may need to concentrate the minerals within the ore. Thirdly, conversion of the mineral to a compound suitable for reduction. So it's important to note that you can't just take those minerals and then reduce them straight away. We have to convert them in a suitable form. Then we obviously have to carry out reduction, because it's about taking those metals in combined form and reducing them to form metal elements. Sometimes we also need to refine the metals if they are of not high enough purity for what we need it for. And like I said, not all stages may be required. So an example would be aluminium production, as we'll see later. So now we're going to look at really two specific examples. We used to actually get you to know all the details to do with zinc production, including all of the equations. So thankfully you don't really need to know that now, but I would say it is still good to be familiar with it, because questions in tests and exams might actually ask you about these specific processes. With sufficient information, you'll need to be able to maybe write equations, or to understand how electrolysis works, or reduction of the metal works. So zinc, in terms of extraction, we extract an ore known as zinc blende, or its name is also known as sphalerite. The main components consist of zinc sulfide, cadmium, lead, silver, so other metal kind of impurities that we can say, but we would be looking at trying to remove them and even commercialize them, so produce these metals for use in other areas. The second step, to concentrate the mineral, we crush and grind the ore into a very fine powder. So any reactions that follow from this, or any physical processes that also occur, like the one we're going to talk about in a moment, it's going to help encourage these processes to occur. So increase physical as well as chemical processes and rates. So the zinc sulfide gets separated from impurities, which we call the gangue, by froth flotation. Just keep in mind, flotation doesn't have an A after that first O. So we use detergents. We call them xanthates, and these work in pretty much the same way as soaps and detergents. Because if we have a look here, we can see we've essentially got a non-polar component here, and then we've got an ionic head, so to speak. So non-polar, polar / ionic. And that's going to help facilitate the mixing of polar and non-polar things, which we'll see in a moment. So here's a diagram of froth flotation. It was the best one that I can find. Just note the little typo there. Here is a diagram just showing you how the xanthate helps to bridge two things together. We have air bubbles, which we essentially can think of as consisting of non-polar gases. Okay. We have zinc particles with the zinc ions, which are positively charged, okay, if we consider the zinc component. And we have the negatively charged ionic head, which is going to form a strong ionic bond essentially between those components. Okay, so you've got strong ionic attractions here, and then what type of interaction would we have between the non-polar tail and the air bubble? Dispersion forces. Excellent. So you can see different polarities, different interactions with different parts of your xanthates. That's represented by pine oil here, okay, because certain oils with their fatty acid ends could potentially act in the same way. So in terms of how this works, we essentially feed in the powdered ore, we mix it with water to form a slurry, we add our xanthate, and we essentially force compressed air through this mixture to form a range of bubbles. And so the xanthate will also help to kind of form a bit of a lather, like soaps and detergents do. We know that the xanthates will help attract those zinc ions in the zinc sulfide, but at the same time as the air is forced through, the non-polar end is going to essentially bind and form dispersion forces with those air bubbles. And because they become quite low in density, they will essentially rise to the top and form what we call a froth. And so that froth essentially, it will rise to the top. The other impurities, the gangue, will settle down to the bottom. So things that are generally heavier or don't have the same attraction with the xanthate. So the froth then can just be skimmed off or separated from the remaining mixture. Okay, so for part 3, conversion of to a form suitable for reduction. So we're going to convert the zinc compound into eventually a form that we can then allow for the reduction of zinc. So the first step that we do is called a roasting process. So that's where we essentially react it with oxygen under high temperatures in a furnace. And it's going to convert the zinc sulfide into zinc oxide. In doing so, it also produces sulfur dioxide, which in the past we've associated as forming a pollutant that contributes to acid rain if we haven't essentially isolated it and we've allowed it to release into the atmosphere. So you might remember some of that discussion based on stage 1, but also this year when we've talked about non-metal oxides, sulfur oxides, nitrogen oxides contributing to acid rain. Thankfully, we've found a use for sulfur dioxide. So it's called the contact process. We can isolate it, we can convert it into sulfuric acid. So this again links into what we've talked about the formation of acids. So the zinc oxide still isn't in a suitable form. And really the key thing is that we actually want to turn it into a solution. Zinc oxide is insoluble, so we want to turn it into a form that is water soluble. So thankfully we can take that sulfuric acid we have produced, we can react it, and we can essentially form a salt plus water. So just to remind you from last year, we learnt about reactions of acids with metal oxides. We can classify metal oxides as basic oxides. They essentially react in the same way as hydroxides in that they are neutralized and they produce a salt plus water. Now in terms of those other impurities, and the key point here is that they are of lower activity, they get removed by the addition of zinc dust. What I always find funny is how in order to make zinc, you need zinc. And it's just like, well, where do you get that, you know? So in this case, we actually need some zinc metal. And what we do is we add it to this solution. This is a metal displacement reaction where essentially zinc, which is more active than, say, cadmium, will displace cadmium ions from a solution of its ions. And what does that actually mean? It means zinc being more reactive is willing to oxidize and give its electrons to cadmium ions, which then get reduced. It's a very simple redox process that we've seen previously. The same thing will happen for silver or for any other metals of lower activity that are also present as impurities. And what we end up with are solid components of these metals, which we can then separate from the solution, and then we can commercialize it, so sell it off to companies that might use it for specific purposes. So you can see that these, I guess, if we link it into topic 2, these would be classified as byproducts, okay? Because we are looking at a chemical industrial process, looking at the manufacturing of metals. So this is where we come to the 4th step, which is reduction. So in this case, we use electrolysis of an aqueous solution of zinc sulfate. So we can see here, we've got zinc sulfate solution. And I've just shown you that we have these components in solution. We have water, which makes it a solution. We have zinc ions and sulfate ions. I've got my power supply up here, negative, positive end. The negative end provides a force to push electrons onto our cathode. And just remember, the cathode is the site of reduction. So you have to imagine electrons are flowing down here, and which of the components in the electrolyte will be attracted to it? To the cathode, yes. Yeah, so zinc ions will be attracted to the cathode, and what's going to happen to the zinc ions? They undergo reduction. So we see a migration of zinc ions, we see the conversion to zinc metal. I know, I'm pretty impressed by that. And over to the other side, we're going to get anions attracted to the anode. Or are we? Now, one thing to point out is that sulfate actually can't undergo oxidation. And part of that stems from the fact that the sulfur in the sulfate exists in its maximum oxidation state. And if you want to confirm, work out its oxidation number. Its maximum oxidation state is equal to its group number. Okay, so you can work that out. So instead, we get water migrating to the anode. Now, it's not an anion, but keep in mind water can undergo both oxidation and reduction. So in this case, water migrates to the anode. Water gets oxidized. What does that actually look like? Well, water produces oxygen, okay? Oxidation can produce oxygen from water, and in doing so, we'll also form hydrogen ions. We lose those electrons, they essentially get fed back in to complete the circuit. So we get two products, zinc at the cathode, oxygen at the anode. So I've just summarized that, and I'm not going to spend much time on this, but here are the half equations. So zinc gets reduced, that's straightforward. Water gets oxidized, so just remember, oxidation is a gain of oxygen, and sometimes you can think of as a loss of hydrogen. So water effectively is losing hydrogen, so that you're left with just pure oxygen. Those hydrogens are lost as protons. And one other thing just to point with that is that the hydrogen ions and the sulfate can go to make some more sulfuric acid. And then that can essentially be fed back into essentially the flow chart back when you have to actually carry out the leaching process. So there's some pretty beneficial processes involved in zinc production. Here's our net equation, just ensuring that the electrons gain equals the electrons lost. So just confirm that that is the correct redox equation, if you can. So alternatively, and I just want to use this because it does talk about some of the less active metals, that you can use carbon reduction. So that is using carbon or a compound of carbon as a reducing agent. Zinc can essentially be taken in the form of zinc oxide and reduced through this method. What it can involve is essentially taking coke, which is carbon or coal, burning it in a furnace with oxygen, with air, to produce carbon monoxide, adding in your zinc oxide solid, allowing it to react and you get the reduction of zinc oxide to form zinc. And remember, oxidation is like a gain of oxygen, so carbon monoxide gains oxygen to form carbon dioxide. And then I had this sort of question here. So most zinc production utilizes electrolysis of aqueous zinc sulfate. And I think it's over 90% of all zinc in the world is produced through electrolysis of a solution. Why is that? Well, firstly, needing an industrial furnace is quite energy intensive. So carbon reduction requires temperatures of in excess of 1,000 degrees Celsius. And how do you get that? Well, you typically burn fossil fuels, and that's going to contribute to CO2 emissions, as we can see there. So the energy demands can be quite similar, but then it's the environmental impact that essentially poses a bigger threat, whereas electrolysis of the solution doesn't have that issue. What I do want to point out at this point is that carbon reduction can be used for the reduction of less active metals like lead or iron, and they work in the same way. So with the last one, or the last part, zinc ends up being produced with a purity of greater than 99%, so we essentially don't need to refine it, and it defeats the purpose because it's going to require more energy to try and refine it, but it's not needed, okay, for most of its intended uses. So aluminium production. So extraction, the ore itself is called bauxite, and Australia, in actual fact, is the largest producer of bauxite. It does contain these main ingredients. So you've got aluminium hydroxide, silica, and your iron oxides. So the key thing is trying to obtain that aluminium. So how do we do that? Firstly, the mineral doesn't need to be concentrated because it's already of a high enough percentage, the mineral itself. So there's no point doing it. But what we do is we crush the ore into a fine powder for similar reasons for zinc production. Conversion to a form suitable for reduction, we react it with a solution of sodium hydroxide and we heat it. So heating will help increase the rate of this reaction. And what it does is it actually reacts with the aluminium hydroxide. And in terms of the other impurities, it either does not react, so the iron oxide doesn't react, and the silica, if it reacts, it actually forms an insoluble compound. So it turns out that only one of the products, which is the aluminium hydroxide, when it forms the NaAlO2, that itself is water soluble, whereas all the other components are insoluble. So that's how we can separate it from all those other impurities. Don't need to know too much of these details, but essentially we reform the aluminium hydroxide because the key thing was just trying to separate the aluminium hydroxide from all the other impurities, and then we heat it in a kiln to produce aluminium oxide, which is what we call alumina. From that point, we then carry out reduction. So we've got the reduction of aluminium oxide as a molten substance. So I've got here the electrolyte is molten alumina in liquid form. I also put here mixed with molten cryolite. So this is a substance that we use to try and reduce the melting point, because you can imagine trying to melt an ionic compound is extremely energy intensive. And typically if you add impurities, it actually helps lower the melting point quite significantly. So I can't remember exactly, but I think you can still get it to about 1,000 degrees Celsius instead of something that is in excess of that. In terms of what happens, very similar to previously. So we've got our carbon cathode or graphite cathode, which is our site of reduction. Electrons get deposited here. The cations are drawn towards the cathode, and then we get the production of aluminium. There isn't anything else present but oxide ions. So in this case, the anions travel to the anode and they get oxidized. So the oxide ions combine to produce oxygen gas. They lose electrons and they get fed back into the circuit. I'm just going to quickly go through these because it just summarizes the half equations and the net redox equation. So this is the reaction that's summarized. We've taken an ionic compound and essentially converted it back to its starting materials that could be used to make it up. That is the metal and the non-metal. So this process could be used as a means of producing aluminium. Maybe to some degree it could be used to produce oxygen. However, one concern is that oxygen likes to react with carbon, and so the graphite electrodes typically will be kind of reacting with the oxygen produced at the anode, which means that they just need to continually be replaced all the time as it reacts with the anode. It'll produce carbon dioxide as the key product. So I've just put here, reduction of an aqueous solution is preferable because it's less energy intensive, therefore it means lower operating costs, but it's not possible for aluminium. And the reason why is because water, like I said, can undergo oxidation and reduction, and water being less active gets reduced in preference to aluminium ions. And so just remember, reduction can involve loss of oxygen, gain of hydrogen. So water essentially then converts into hydrogen gas, but it also produces hydroxide. So finally, electrolysis of melt or a molten ionic compound is required for anything that is aluminium or above on the metal activity series. And that's just one of the key ones to remember, I think, for exams and for test purposes. Last bit, again, refinement isn't needed because aluminium gets produced with a high enough concentration. So, lucky last slide, guys. We're coming back to this diagram here that I annotated on, because what it highlights is anything that is aluminium or above requires electrolysis of a melt. And I think that's something that's going to be important for you guys to note. There's only one electrolysis of an aqueous solution, which is for zinc. I have water here as a comparison to show you that anything above, water is going to undergo reduction in preference to aluminium or above. You've got chemical reduction that can be used using carbon or carbon monoxide. Okay, that might be through the addition of some heat as well. And then you've got a range of metals which typically are uncombined, so we don't need to worry about these methods of reduction.